Okay, welcome back. Thanks for coming. I know that you might be feeling all thermoed out since we had an exam yesterday. But because we're drinking from the fire hose in this 6-week sort of time frame, it is time to start thinking about the final exam as well. So we wrote nominally the second midterm yesterday. So about 2 weeks from yesterday, right? So not next week, but the week after, Tuesday, August 9th, is when I'm tentatively scheduling the final. So I will need your help. I'll need some input from you about what time works. So unlike the midterms, which were 10 multiple choice and 2 long answer problem, the final exam will be 10 multiple choice and 3 long answer problems. Good news here is that the final exam will have equally weighted parts, so that the multiple choice actually ends up being weighted a little bit less than it is in the midterms. So I think it's worth 30% in the midterms and 25% in the final. So if we start at 6:30, so because it's longer, the exam will be longer. So we'll still get the same amount of time for that extra long answer problem. So there'll be an extra 5-minute break after problem 2, and then an extra 40-minute problem. Now, if you have accommodations, then you'd scale that time accordingly. But that means that if we start at 6:30, we won't be finished until 9:20. So I will send out an email to the class just asking for thoughts about when a good start time on that Tuesday will be. And again, I can be flexible if different people have different start times, because I understand that that it's certainly possible that people have conflicts with things like employment or other classes or something. So, but my thought process here was we could have written the exam per the university on Friday, Monday, or Tuesday. So I didn't want to do Friday because I think it makes sense to give you that extra weekend to study. And, that gives us a little more time between the midterm and the final. But it also, the Monday didn't work personally for my schedule, although if people end up writing that day, then we can certainly do that too. So if you have any conflicts for that Tuesday, August 9th date, or you would prefer to write on the 8th of August, which is the Monday, or I believe the 5th of August is the Friday, please let me know if you would prefer those times. So what's left? The answer is not that much. So today, I guess we have a little bit of a choice. We could just do turbojet engines today, and then maybe take a break, because I know we've had a lot of thermal this week, and then do heat pumps and refrigerators. Would probably take about half a class on Tuesday, and then we'd have a class and a half for review. Or we could go ahead and try to push through everything today, and then have 2 full classes, which is over 6 hours of review. So we'll have some choice, and I guess maybe I'll take a poll after we do the 2 sections on turbojet engines to see if people want to continue, or if you'd rather just go to bed. So that's what's left. So we're just about done, right? And we're still thinking about going, cycle by cycle, right? But it's still always the same principles that apply when we're doing these different cycle analyses, right? So we're still thinking about, how do we characterize the cycle? Are the different processes open or closed? And what's the fluid? And I think if we can categorize the different cycles by their answers to those 3 questions, then we can kind of apply the same solution method to each one of these problems. And I know, at least for me, that makes it much easier to solve these kind of problems instead of trying to memorize, hundreds of different permutations or however many there are, right? I think of every problem in thermodynamics as kind of being the same problem. We just have different answers to these 3 questions. So last class we talked about Brayton cycles. And when we think about those 3 questions, right? So how do we characterize the cycle? This is a heat engine. So it takes heat in and turns it into net power, which means we characterize it by its thermal efficiency, right? So the net power over the heat rate in, or we can think about it as a backwork ratio, as the magnitude of the compressor power divided by the magnitude of the turbine power, right? That's kind of acknowledging that the power plant is the first consumer of the power plant. So the second question is, when we look at each process, is it an open system or a closed system? So for this cycle, because we move, each process happens in a different place, like an assembly line. That means that it's a series of open system processes, right? That means we use the open versions of the first law and the second law. Our third question is, what's the fluid? And here the fluid is air, or I guess some other ideal gas. And that's what makes it different than a Rankine cycle, because it's kind of very similar to a Rankine cycle, because the answer to the first two questions are the same, that it's a heat engine with open processes. But because it's a different working fluid, then we fix the states differently. Right? If I was drawing a TS diagram, at least of a 4-component Rankine cycle, this is what it looks like. We go through this ideal compressor, then we add heat, then we go through an ideal turbine, then we reject heat. If we try to do the analysis, because it's a series of open systems, we apply the open version of the first law. We make all of these assumptions for the different components, right? Hopefully assumptions we're getting used to making, right? And we find that if we're trying to find work, it's m dot times h in minus h out. If we're trying to find heat transfer, it's m dot times h out minus h in. And we let the first law deal with the signs, understanding that heat in is positive and work in is negative. Right? But now we get to the point where we say, what's the fluid? How do I fix these values of h's? And because it's an ideal gas, then we need to use the ideal gas law, right? That might be useful as we move from state to state. But my argument to you, and I've been teaching the class for a long time, so I think it's a good argument, is that when you have cycles where the working fluid is an ideal gas, you need to be able to identify where any isentropic processes are. So where are the processes where you get work and at least usually don't have heat transfer, right? So where are your ideal turbines and where are your ideal compressors inside the cycle? That's where you're going to be able to use these different expressions. And if it's a variable heat transfer problem, or a variable variable specific heat, then you'll apply, because it's an open system and we normally know pressure ratios, you get these relative pressures, PR over PR, and you'll get this pressure ratio. So if you know the compressor pressure ratio, you can use that to find PR at the exit of the compressor. And then you can go to table A22 and interpolate backwards, right? Usually we're maybe more used to saying, oh, I know the temperature of the ideal gas, and then I interpolate from left to right to find H. But out of these isentropic processes, what happens is I'm trying to find the PR value, and then I'm interpolating from right to left to find H. Now, if it's a cold air standard problem or constant specific heat problem, it's a little different, because the first law asks us to find delta H, but we're not going to find the individual H's. We're going to assume that delta H is approximately equal to Cp times delta T. And if we know that, we can find Cp, that'll be on table, I believe, A20 or A20E if it's an imperial problem, right? And then what we're trying to find when we go through that ideal compressor or that ideal turbine, what we're trying to find is what's that isentropic outlet temperature, right? And then what we're looking for is an equation that has K up in the exponent, right? These are the equations for ideal gases. And let's see if I have it open here, right? So here, if I go to, right? So if I go to course information on the My Courses page, right? I like to look for this exam equation sheet. This is the one that I wrote. If you were writing the exam in person, this is the only reference material you'd get aside from the tables, right? And here we can say that if we have ideal gases, then I can use all these equations, right? But if they're isentropic ideal gases, then I can use these equations. So if it's constant specific heat, I use one that has K in it, because anytime I have an equation that has Cp, Cv, or K, which remember is Cp divided by Cv, then in order to write that equation down, I have to have made the assumption that specific heat is constant, or I guess I would be integrating that specific heat value over the range of temperatures, which we just wouldn't do, right? That's why we have the tables, right? But if you're not using constant specific heat, if you want a more accurate answer, you want variable specific heat, you got to use table A22, and then you use either an equation that's got PR over PR or VR over VR, right? And those are things you look up in the tables, right? Now, which equation do you pick, right? So my argument is that if it's an open system, you're probably going to know pressure ratio. So if you're talking about a Brayton cycle that's got a bunch of open systems in it, you're probably going to know pressure ratios. So if it's constant specific heat, you're going to use this equation. T over T is equal to P over P to the power of K minus 1 over K. And if it's variable specific heat, you'll use P over P is equal to PR over PR. But when we did internal combustion engines where the processes were closed, then we knew volume ratios. So I would go T over T is equal to V over V to the power of K minus 1. Or this equation that's got the ratio of VRs is equal to the ratio of Vs. There's also this equation in the book, and we put it on the equation sheet, but personally, that's not an equation that I really used myself. Okay, then we talked about how do we improve the performance of these Brayton cycles, right? And one of the ways we can do this is we take the hot exhaust gas and we transfer some heat from there into this pre-combusted fuel or pre-combusted fluid, right? So we're trying to reclaim some of the heat that we would otherwise lose to the environment, right? And we call that regeneration. And then we can do reheat, just like we did in Rankine cycles, where we can split our turbine into two turbines and heat the fluid back up in between. That gives us more enthalpy in the fluid as it goes into the second turbine, which means we can harvest a little more mechanical power out of that second turbine than we otherwise would have if we just went straight through one turbine. Now, unlike Rankine cycles, backwork ratios are relatively high in Brayton cycles because it turns out it takes more work or more power to increase the pressure of a gas than it does a liquid, because gases are incompressible, right? So we want to reduce the power consumed by the compressors, and one of the things we do there is we split that compression process into two parts and we cool the fluid in between. And that increases our net work, not by increasing the power we're creating, but by reducing the power we're consuming. So the net work goes up. Right? Now, then what we did, right, is we took all of those parts and we put them together in the last example we did in the last class. Now, it's pretty complicated, but definitely something that I've asked on final exams before, to walk through a process like this. Now, it wouldn't have been as much work as what we did in the example last time, because you wouldn't get a state table that's mostly empty, like it was in the example problem we did before. Instead, you'd get a state table that's kind of mostly filled out, but we'd kind of expect you to be able to say, find out what the isentropic efficiency of the first compressor is, or maybe one of the turbines, right? How do you deal with the regenerator? How do you find, H5, and how do you find H10? So those are things that we can ask you. But, so I guess the message here is you're probably going to see some complicated stuff on the final. Try to, when you look at that problem, try not to say, like, I don't know what's going on in this problem, it's too hard. Instead, look at it, look at the state table, notice that it's mostly filled out, and then say, oh, I know the process of how to do this. Most of this is going to be symbolic work, right? Which doesn't take all that much time if I know how to do that. So really focus on, picking the right equation, making the right assumptions so you can get the symbolic equation. Okay. So that's kind of the high level overview of what a Brayton cycle is. And it leads us into turbojets, right? So turbojet engines are jet engines that you'd see, anytime you fly anywhere. Sometimes I guess when you fly in and out of Rochester, you have turboprop planes. But if you have a jet engine, this is probably what's hanging under the wing there. And it's kind of cool because the core of this, as we'll see, is a Brayton cycle. But there's some extra things that are going on. Right, so I like to ask this question when we start to look at these turbojet engines. I like to ask people, what is it that we need in order to fly? Right, now, you can think in your head if you don't want to answer out loud, right? But if I ask my kids this, because sometimes I run my lectures by my kids because they get a little bit interested in what we're talking about here, right? And I like to put Disney pictures and stuff in here, right? So what my kids would say is what you need is faith, trust, and pixie dust, or at least they would have a couple years. Well, maybe my 4-year-old would still say this, right? Because that's how you fly in Peter Pan, right? But it's not actually how you fly in real life, right? What you'll learn in fluid mechanics is that the design of a wing is actually really important. The shape, the cross-sectional shape of this wing is really important for how it flies. Because how an airplane flies, yes, lift is super important, right? So that's what happens in this particular problem. What happens, the way we generate lift is we make this wing that has a very special shape. And when air flies over it or is pushed over the wing, what happens is we generate high pressure air underneath the wing and low pressure air on top of the wing, right? And that comes from the shape of the wing. It's super cool, right? And then what happens is you've got high pressure underneath the wing and low pressure on top of the wing, so you have a net force up on the wing. And if that net force is high enough, then you can get this, heavier than air machine that's full of people and their luggage to fly through the air, right? And it's kind of a triumph of human ingenuity, right? But how do we get lift, right? In order to get lift in this picture, we need air to be flowing over the wing at a high rate of speed. So in order to do that, we need to generate thrust, right? And that's the job of the engine, right? We're going to talk about turbojet engines, but it's true of propeller planes too, right? Is you're trying to essentially push the plane forward fast enough so that even if the air is still, or even actually if you've got a tailwind, right? So even if the air is kind of going the wrong direction, the plane is moving fast enough relative to the air that it looks like, if you're a crazy person standing on the wing, it feels like the air is really whipping into your face, right? So the important thing here that, in terms of this course, right, is the thrust that gets generated by this engine, right? So it's, faith is still kind of important, right? So this is, I sometimes joke with my client, I went to school with people that design airplane parts now, right? So I've seen them at their best and probably at their worst, right? So it's still nice to have a little bit of faith, right? A pixie dust maybe doesn't hurt either, right? But it's thrust that we're after from that turbojet engine, right? So it's pushing the plane forward so that the air is flowing over that wing. Right? Now this part's not going to be on the exam, but I still want to talk about it because I keep harping on the fact that, the first question we got to ask about all these cycles is, what's the energy benefit and what's the energy cost? How do we characterize the engine? And you're not going to be asked for a thermal efficiency on a turbojet engine, but I still want to walk you through what the benefit here is. Right? So thrust is defined as the change in momentum over time, right? So momentum is mass times velocity, right? Time delta t. right? Or we could say mass over delta T times velocity out, right? So that's the air going out of the jet and the air going in. So what the jet is trying to do is push air very fast out the end of the jet, right? So it takes in air and it pushes it out faster, right? So mass divided by delta T, right? If we take the limit as delta T becomes infinitesimally small, becomes a mass flow rate, right? So the mass flow rate times the velocity of the air out minus the mass flow rate times the velocity of air in is equal to our thrust force. Right now, if the jet has one air inlet, right, where it's sucking air in, maybe you've seen those super slow motion, right? They're testing the blades, right, and they chuck like a frozen turkey or something into a jet engine. You should check that out because it looks awesome on the high-speed videos. Right, there's really only one mass flow rate because there's only one inlet and one outlet here. So the thrust force is the mass flow rate times the outlet velocity minus the inlet velocity. But if you think about thermal efficiency, right, we want this in terms of power, right? So how do we get from a thrust force to a thrust power, right? So now we know that this should be in power. Power is kilowatts, right, which is kilojoules per second. And what we have is thrust as a force, right? So kilonewtons. So kilonewton meters is kilojoules. So kilonewtons times meters per second is the same as the thrust force times the velocity, right? So if we take the thrust force times the velocity of the jet, then you can get a thrust power. So if you're looking for thrust power, you take your thrust force, the mass flow rate times V out minus V in, times the velocity of the jet, and that would give you the power that's developed by the engine. Notice this is different because now this is not, every other time we've talked about power, sort of the reason we don't ask you about thermal efficiencies for these turbojet engines is because this is not mechanical power in the way we've thought about it for all the other engines, right? So it's not a rotating shaft, right? Which we get an electrical engineering friend to put on an electrical generator there, turn that rotating shaft into electrical energy, right? So this is thrust power, so the power of that jet that's coming out of the back of the jet engine, right? Now the energy cost, well, this is just like your automobile, right? Or your Brayton cycle or your Rankine cycle. It's the heat in, right? So here we're burning jet fuel, right? So we need chemical engineers, right? Because they're going to take oil, right, and separate it into all these, wonderful different chemicals, one of which is jet fuel, right? So it's still going to be heat in. We're going to burn that jet fuel at a particular, it's going to give us a certain amount of heat or heat rate, right? And that'll give us our thermal efficiency, right? But we don't really talk about it this way in the textbook, right? So I'm never going to ask you about thermal efficiency of a jet, but I just want to show that it's possible to still think about it like this as an energy benefit divided by an energy cost, right? One of the tricky things about jet engines, well, maybe there's a couple of things. So first, your airspeed matters. So maybe you've been on a plane where they tell you, oh, we're running a little bit ahead of schedule because, we've got a little bit of a tailwind, right? So that matters. But for us, we're always going to assume that the air is still, right? And we're usually going to think about the problem as if you're that crazy person standing on the wing, right? So that it feels like the velocity of the air is whatever the jet velocity is, but just in your face instead of right. So your frame of reference is that crazy person standing on the wing. So this is, at least schematically, how we can think about a turbojet engine in terms of a thermodynamic device, right? So it's got a diffuser at the beginning. So because, the jet is screaming forward, right? But we're going to think about it as if we're standing on the jet, right? From the perspective of the engine, it feels like the air is coming into the diffuser with some form of kinetic energy because it feels like it has a velocity, even though the air is still, for somebody, standing on the ground, it feels like if you're standing on the wing that it's really windy, right? So we're going to take that kinetic energy of the air and turn it into enthalpy. That's what happens through the diffuser. And then in the middle, we have this Rankine cycle, right? Well, I guess to back up, right? So we're going to take that air and it's got some inlet velocity, right? And what we're trying to do, instead of maximizing the shaft work, right, or the power from the rotating shaft in the system, we're trying to maximize the thrust, right, at a given mass flow rate. So the way we do that is we try to get as much velocity coming out of the nozzle as we can, right? So that's the job of the turbojet engine. And if we remember that, we'll avoid one of the common pitfalls that people have, right? So the job here is to maximize that outlet velocity from the jet. Now, at the core of this system is a Brayton cycle, right? So there's this compressor, which, you know, we might think about as ideal in some cases, or maybe we get an isentropic efficiency. Then there's a combustor, right? So there's this air-fuel mixture that we burn, right? Although we're going to pretend that it's all just air and we're adding heat. And then there's a turbine, right? So after we add heat, we've got a lot of enthalpy in this fluid. We're going to take some of that enthalpy out of the turbine, but try to leave as much enthalpy as we can here at state 4, because our job for this engine is not to maximize the turbine power. That's why turbojets are different than Rankine cycles and Brayton cycles, because the job here is to maximize the kinetic energy at the outlet of the nozzle. Right? So we solve this mostly like a Brayton cycle problem, except there's a nozzle and a diffuser, right? And when I tell you that, the hairs on the back of your neck should stand up a little bit, right? Your spidey sense should be tingling, because that means kinetic energy, at least when we're on the outside of the jet, right? So when we're at a state that's not touching the Brayton cycle, kinetic energy is important, right? That means units are going to be a problem, right? So how do we solve this problem? We start at the diffuser. Right? So at the diffuser, what the diffuser's job is it's saying, well, if this air is coming in with some velocity, why don't I harvest that velocity to increase the enthalpy before I even get to the compressor? So it looks like, as in the labeling here this is one of those things where I think the textbook tries to help us, because it's still state 1, 2, 3, 4 here as we go through the Brayton cycle part of the turbojet. So they try to keep that numbering the same. But that means that they needed something else to call the inlet of the diffuser, and they call it state A, right? So usually we stick with that nomenclature. So as we move from A to 1, it's kind of doing the same thing as a compressor, in that it's increasing the enthalpy of the fluid. But the compressor increases the enthalpy of the fluid by putting mechanical power in. The diffuser increases the enthalpy of the fluid by harvesting that kinetic energy, right? So here we're trying to maximize the enthalpy at the exit of the diffuser. So here, this means we have to do a first law analysis on the diffuser, right? So we're going to say that it's at steady state, that it's got one inlet and one outlet. We're going to neglect potential energy changes, but we can't neglect kinetic energy changes, because the whole job of this component is to trade kinetic energy for enthalpy. We are going to say that this component is both adiabatic, so there's no heat transfer, and it's passive. There's no fan blades in here. It's not a turbine. It's not a compressor, right? So there's no shaft work. But the thing we're going to do here is we are going to, when we think about these things in turbojets, we're going to cancel out one of the kinetic energy terms. Now, what it looks like here, it looks like we're saying that the exit velocity is 0, right? We know that's not true. Really, what we're saying here is that at the inlet, both enthalpy and kinetic energy are important, because the kinetic energy is high. But at the outlet, or the exit, well, enthalpy is certainly important, but we're going to assume that we've dropped that kinetic energy low enough that it doesn't matter anymore. Right? And remember, the velocity here even though it gets squared, it has to be pretty high to matter, because even though this looks like it's velocity squared over 2 in metric, this would be in joules per kilogram instead of kilojoules per kilogram if my velocity was in meters per second. So then I'd have to divide not just by 2, but then I'd have to convert 1 kilojoule is equal to 1,000 joules. So I divide by 2,000. So that number gets small quickly, right? So we're going to assume that the kinetic energy is small enough that we don't really care about it at the exit of the diffuser. So if we do that, then what it says is, oh, at the inlet, enthalpy and kinetic energy are important, but at the outlet, it's only enthalpy that matters, right? Now, unfortunately, you're still going to have to do problems in the imperial unit system here, right? Now, the units are, no matter what, this kinetic energy term is going to be tricky because, like I said, you're going to probably still have to deal with units here because this is probably going to end up in joules per kilogram. Well, this, when you look it up in the textbook, will be kilojoules per kilogram, right? So the units still matter in metric, but it's even more tricky in imperial because first, you got to divide by GC just to get the right quantity, energy per unit mass, but the energy here is going to be in feet per second squared if your velocity is in feet per second, right? Or sorry, this term is going to be in foot-pounds per pound mass, right? So not only are you going to have to divide by GC, but if the velocity is in feet per second, you're also going to have to multiply by 1 BTU per 778 foot-pounds force, right? So that kinetic energy term. So the diffuser, this is one of the places where people get tripped up, is dealing with the units, particularly, of the kinetic energy on the diffusers and the nozzles, right? So the units here are important. So that's how we go through the diffuser. Next, we're going to go through the Brayton cycle. Now, mostly this is the same as a normal Brayton cycle, but there's a wrinkle here when we get to the turbine, right? Because normally when we go through a Brayton cycle, a couple of things are true, right? The inlet to the compressor, or at least the first compressor, is the atmosphere, right? And the outlet from the last turbine is also the atmosphere. So those two things have the same pressure, but that's not true here, right? It's not true here because neither of those two components touch the same reservoir. They're not touching the atmosphere because one is touching the exit of the diffuser and the other is touching the inlet of the nozzle. So those pressures are not equal, right? That's the first thing that's tricky. So we can't solve these things by assuming that, oh, the compressor ratio is 10. So that means that going through the turbine, the pressure ratio must be 1 over the compression ratio, right? We can't do that, right? So instead, we remember that the job of the turbojet engine is to maximize this outlet velocity. And in order to do that, we need as much enthalpy sticking around at state 4 as we can, right? So we're only running the turbine so that we can run the compressor, right? Although maybe you'd argue maybe in a real jet, it's not just running the compressor, it's running the compressor plus whatever systems are on board, right? But, right, for our purposes, we're going to say the turbine is only running the compressor. So the backwork ratio of the Brayton cycle here is equal to 1. So when I find the compressor power, I know that the turbine power has the same magnitude, right? But the opposite sign if I'm using the first law to find these things, right? So this is another place where people consistently make mistakes on final exams when we ask about these turbojet problems, is that they forget, they make the pressure ratios the inverse of each other, like in a normal Brayton cycle. But really what you have to do here is make the backwork ratio equal to 1. So if you see a problem, a turbojet problem on the exam, the first thing that I want you to do is write down kinetic energy units and then write down backwork ratio equal to 1, right? Or if you like, magnitude of the compressor power is equal to the magnitude of the turbine power. Or you could write down turbine power plus compression or plus compressor power is equal to 0, right? So for these components, right, this is just going to look like a Rankine cycle, or a Brayton cycle, but actually symbolically looks the same as a Rankine cycle too. All of the components will be steady state. They're all one inlet, one outlet. There's no fancy like splitting of the mass here, right? We're going to neglect kinetic energy inside the system. As long as we're not a state that's touching the outside, we're going to say that the kinetic energy can be neglected. We're going to neglect potential energy changes. And then I'm going to look through these components and I'm going to say, well, some of them are adiabatic, like the turbine and the compressor. But that heat addition, we're going to say, is passive, right? So that there's no power, right? We're, again, going to neglect friction losses and heat losses throughout the system, right? So here, inside the Brayton cycle, we're going to get equations that we're used to. Turbine power and compressor power, m dot times h in minus h out. Heat rate in is going to be m dot times h out minus h in. Right? But the important thing here is that the magnitude of the turbine power is equal to the magnitude of the compressor power. That is going to be how you will solve for H4 at the exit of the turbine. Right? So it's a little different than a normal Brayton cycle where you would find the ideal outlet of the turbine and then use the isentropic efficiency to get to the end, right? Here you're just going to say, oh, the real compressor consumes a certain amount of power. Well, that must mean that the real turbine produces that same amount of power. Right? So that if the back work ratio is equal to 1, then you get that m dot times h in minus h out on the compressor side is equal to the negative, so equal magnitude but opposite in sign, of m dot times h in minus h out of the turbine. Right? The mass flow rates are the same because the whole system is steady state, one inlet, one outlet throughout, right? And everything is arranged in series, right? So here we can get this equation, and typically we'll be solving for H4 from this equation, right? So here you could say that H4 is going to be equal to H1 minus H2 plus H3, right? Typically, and if there's isentropic efficiencies, it's the real compressor power that's equal to the real turbine power. So that gets us up to state 4, right? But we're not done the cycle yet because we still need, the whole reason that we're doing this thing is the nozzle, because we want to maximize that velocity at the outlet of the nozzle. We want to get as much velocity at state 5 as we can, which is why we tried to keep as much enthalpy as we could at state 4, because the nozzle's job is to take as much enthalpy from state 4 as it can and turn it into kinetic energy. Right? So again, kinetic energy is going to be important here. So the units are going to be a pain, right? But don't let that intimidate you, because once you do it 2 or 3 times, then it's not too bad. Well, 2 or 3 times in metric, and then maybe 3 or 4 times in imperial units, because it's a little trickier there, right? So here for the nozzles, we'll say that we're at steady state. One inlet, one outlet. No potential energy change. Both adiabatic and passive. So far looks just like the diffuser. And just like the diffuser, one of these kinetic energy terms goes to 0. Just like the diffuser, it's the one that touches the Brayton cycle. But unlike the diffuser, it's the inlet kinetic energy that goes to 0 and not the outlet kinetic energy. Right? So here we're going to be solving for the exit kinetic energy, which is kinetic energy at state 5, at least in the picture that we looked at. So now here we're typically solving for the velocity at the exit. That's one of the things that, or I guess the problem could ask for the kinetic energy at the exit, right? Remember again that H is going to be in, if it's metric, kilojoules per kilogram. This velocity squared over 2, if the velocity is in meters per second, is going to be in joules per kilogram. So what you got to do here is multiply by 1 kilojoule divided by 1,000 joules. So you're probably going to divide this by 2,000 and not 2. You're still going to have some problems with imperial units, right? And it's always worse with imperial units, right? And now we're not just dividing by 2 on the kinetic energy term. We got to divide by 2 GC, and that gives us the right quantities. It gives us energy per unit mass. but it's not BTU per pound mass. That's what we're going to look up in the textbook. It's foot-pounds per pound mass. So probably, if your velocity is in feet per second, you're going to have to multiply this by 1 BTU divided by 778 foot-pounds force. Right? So it's always a little harder in the imperial units, but it's still this kinetic energy term that's going to give us problems no matter what the unit system is. Right? So we got to remember, if we're solving for kinetic energy, or if we ever had a problem where we were solving for potential energy change, we still have that same problem with the units. Right? So here, if we're just drawing or writing down the equations that we have for this turbojet engine, if I can make the assumptions that I would normally make, compressor power and turbine power are still going to be m dot times h in minus h out. Heat rate in, still going to be m dot times h out minus h in. At the diffuser, it's at the inlet, I've got enthalpy and kinetic energy. I got to add those two up to find the enthalpy at the outlet of the diffuser, which is the same as the enthalpy at the inlet to the compressor. And if I'm trying to find the nozzle velocity or the nozzle kinetic energy, that's going to be the change in the enthalpy across the nozzle. Right? Now, units are going to be important, even if it's the metric system, which is generally more friendly, I think. Right? It's still going to be a problem with units here. Right? You notice, I had an old professor, and he would always tell us that, it's only about 10% of what the professor says that's actually important for your exam. And the professor, who is the person that writes the exam, thinks that the things they say multiple times are the important things, right? So there's a couple things that I think are important here. One is you got to not mess up the kinetic energy units, right? And two is you got to remember the magnitude of the compressor power is equal to the magnitude of the turbine power, right? You'll notice that throughout all these lectures, I have a slide like this for all of the cycles. Because it's an open book exam, printing those things out might not be a bad idea, but you also got to remember this is just the general shape of what we're expecting, because I could give you a compressor that has some heat loss in it and then Q dot sticks around, right? So you got to know how you get to these equations, but knowing the general shape of what they should look like, I think is usually pretty useful, right? The equations do change slightly when we're using imperial units, right? Because now it's not velocity squared over 2, it's velocity squared over 2gc, and the conversion factor becomes different. Now, on both of these slides, I don't write down the conversion factor because the conversion factor is a function of the units of the velocity, right? So if I give you the velocity here in feet per second, then the conversion factor is going to be times 1 BTU per 778 foot-pounds force. But it's going to be something different if I give you the velocity in miles per hour, right? So I don't write the conversion factors in the equations because I want the equations to be, somewhat general, right? So you have to look at the units and figure out what the conversion factor is going to be, right? But usually it's going to be 1 over 778 for imperial units and 1 over 1,000 for metric units. Again, we're not going to ask you this on exams, right? So on the final exam, I will never ask you for the thermal efficiency of a turbojet engine, but we could still think about that in the same way that we think about the thermal efficiencies for all the other engines, right? Where it's the energy benefit over the energy cost, right? So, but even though I'm not going to ask you this equation, I think it's important to kind of understand the concept here, because the difference between the turbojet engine and all of the other heat engines that we look at, right? All of those other engines were trying to maximize the net work or the net power. But here, the thing we're really trying to maximize is this velocity at the exit, right? And if you remember that, then I think you probably have a better chance of remembering that the back work ratio here is 1, or that the power consumed by the compressor has the same magnitude as the power produced by the turbine. Now, generally, there's not too much different for different turbojets, but there is one thing that we can do, right? And I haven't seen the new Top Gun movie yet, but I remember my dad had the VHS copy of the old Top Gun movie that we would watch frequently because he, just installed this new sound system in whatever that was, the late 80s, early 90s, or whatever it was, and we would just listen to Top Gun over and over again, right? And in those military aircraft, so not in a commercial aircraft, but in military aircraft, you might also have an afterburner, right? An afterburner is basically reheat for a turbojet engine, right? So instead of one, well, maybe it'll make more sense. But really what we do here is after the turbine, remember before we get to the nozzle, what we want is we want to get as much enthalpy into the fluid as we can, right? That's why the backwork ratio was 1. Right? But maybe there's some applications where fuel efficiency is less important than, pure performance, right? Or pure power generated by thrust power generated by the engine, right? So typically this is something on military grade aircraft, right? But you don't see, commercial airliners are far more concerned with fuel efficiency versus, maximum speed, right? So one of the ways we could increase the enthalpy between the turbine and the nozzle is by burning more fuel, right? So this is what an afterburner is, right? It was also like, like one of those sweet Atari games probably, or maybe it was the original Nintendo. I don't know that it was for, right? But afterburners, it also sounds cool, right? But its job is to, when you flick it on, you burn more fuel, right, which puts more energy in the form of enthalpy into the fluid so that you can extract more enthalpy out of the nozzle and get more velocity, right? So just because you have the capability to do this doesn't mean you're running it all the time, but it gives you the opportunity to add thrust if you need to, right? Now, if I was drawing a TS diagram for an afterburner system, at the beginning it looks the same. This is an isentropic diffuser, an isentropic compressor. We're still adding heat through the combustor. We still go through the turbine. This one looks isentropic. But then, right, in between, we add heat and then go through the nozzle, right? Whereas in the normal system, we would just go through the nozzle here, right? So I think of this as the same as reheat. It's just instead of being in between two turbines, we're in between the turbine and the nozzle. But you see here that the nozzle on my TS diagram does the same thing as the turbine, right? It reduces the enthalpy, right, and drops the pressure, right? But it does that in service of generating kinetic energy instead of generating mechanical power. So that is the end of the introductory part of these turbojet engines. But what we'll do is we'll come back for an example in, well, let's come back at 7:25, so maybe 7 minutes or so. I will see you in a bit. All right, welcome back, everybody. So we introduced the idea of these turbojet engines last class, right, or over the last hour or so. And we found out that really the idea here is to maximize the thrust, right? Which for us means trying to get as much velocity out the back of the engine as we can, right? So, if you were looking at the jet from the ground on a stationary frame of reference, the jet is moving through the air. We're going to assume that the air is always still, right? But we're going to think about this problem as if we were a person standing on the wing of the plane. So even though the air is still in a stationary frame of reference, in that moving frame of reference, it really feels like the wind is blowing really hard in our faces, right? So don't try that at home kind of thing, right? Now, because we're trying to maximize the thrust, really what that means is we're trying to get as much velocity out the exit of the nozzle as we can. Right? Now, in the middle of this system, between the diffuser and the nozzle, is a Brayton cycle. But it's a little bit of a special Brayton cycle because it does not have equal pressure ratios or the reciprocal of the pressure ratio through the compressor in the turbine. Instead, what we have is a case where the backwork ratio is 1, right? So the magnitude of the compressor power is equal to the magnitude of the turbine power. And as we go through the example, we're going to see why that's important, right? So that'll let us get H4, but also, as we'll see, it lets us get P4 as well, right? If we have a metric problem, we're going to assume that this is how we calculate this particular, or this is the result of the first law on all the different components, right? Remembering that the units are going to be tricky, even if it's metric. We're probably going to have to divide that velocity term by 1,000, right? And if it's imperial units, right, the equations get a little bit trickier because we got to divide by GC, and the conversion factor is a little different because we're probably going to have to multiply by 1 BTU per 778 foot-pounds, provided the velocity is in feet per second. So what we're going to go through now is an example problem for a turbojet engine, right? So here we have a turbojet engine where we're given some state information, we're told the mass flow rate, we're given the compressor pressure ratio, and we're told, sometimes it tells us this in a bit of a tricky way. It'll say the maximum temperature inside the engine, right? So I need to know how to draw my TS diagram so that I know what the maximum, where the maximum temperature is. It's always before you extract work from the system, right? So what are we told here? We know that CP is 1 kilojoule per kilogram. We're also going to say that K is approximately 1.4. We know the compressor pressure ratio P2 over P1 is equal to 11. Right? We're asked to find the temperature and pressure data, so we want to fill this out, and we want to know the heat rate in and the velocity at the outlet. Right? I think in the notes I go through how to do this both as constant specific heat or as variable specific heat. I won't do it both ways here, but if you have a preference, you can type it in the chat because I can do it either way. I don't care which way that I do it, but I won't do it both ways here. But I believe it is done. If you go through these notes, you start to see both ways, cold air standard and variable, so constant specific heat and variable specific heat. So does anybody have a preference? Okay, I don't see anything in the chat, so I will go with constant specific heat because I think it's a little bit faster. Right, but I'll try to note at least the equations of maybe how to do it the other way. My preference is always to do the symbolic parts first. This I'm not going to do because we're not going to find that on, we're not going to ask you this on an exam, so I won't go through getting the thermal efficiency of the engine. Right, so here, if I want to know Q dot in, right, so for part B, I do the first law. So first I got to pick my control volume over here. I guess most formally, I would do conservation of mass, dm by dt is equal to the sum of m dot in minus the sum of m dot out. But this is steady state, one inlet, one outlet. So m dot in is equal to m dot out. I only have one mass flow rate here, actually through the whole problem, because all of these components are one in, one out, and they're all aligned in series. So there's only one mass flow rate in the problem, which makes sense because they only gave us one mass flow rate, right? So this is 25 kilograms per second. But it asked me for the heat transfer rate. So then I'm going to do the first law. So dE by dt is equal to Q dot minus W dot plus the sum of m dot in h in plus, I look at the units here, and because it's a metric problem, I'm going to leave this as v in squared over 2 plus gz in. So there's no GCs in this problem because it's not imperial. M dot out, h out plus v out squared over 2 plus gz out. Right? This, all my components are at steady state. They're all one inlet, one outlet. I'm going to neglect kinetic energy changes and potential energy changes for the combustor. And the combustor is going to be passive. So if I'm trying to find my, and this is probably what you expected, right? Hopefully at this point we're starting to get to the point where, you know, where we have these things that we're expecting. Q dot in is equal to m dot times h out minus h in, which is equal to m dot times h out is state 3 minus h in is state 2. So this is my symbolic solution for part B. The good news is I know the mass flow rate. The bad news is I don't know H3 or H2. The other thing here, I guess, is because I've already said I'm going to do this problem as constant specific heat. So then actually my equation becomes m dot times Cp T3 minus T2. So because I'm doing this problem as a constant specific heat problem, well, I never would have cared about U in this particular, like specific internal energy in this problem, right? I'm not going to care about the individual H values. All I want is temperature and pressure for all these different states. All right, so this is Q dot in. Part C asks me for the velocity at state 5. And for this, I'm going to have to do a first law analysis on the nozzle. Now the equation stays the same, right? It's dE by dt is equal to Q dot minus W dot plus the sum of m dot in H in plus V in squared over 2 plus GZ in minus the sum of m dot out H out plus V out squared over 2 plus GZ out. Both of the, no, I lied. I was going to say both of them are divided by GC, but that is not the case because it's a metric problem, not an imperial problem. Now, here for the nozzle is going to be at steady state, adiabatic, passive, one inlet, one outlet, no potential energy change. And now I got to think about the nozzle, right? So I know that kinetic energy is equal to 0 everywhere inside the nozzle, right? Here, kinetic energy is not equal to 0. So I'm going to get rid of, for the nozzle, that means the inlet kinetic energy is equal to 0, but the outlet kinetic energy is not equal to 0. That one survives. So here I'm going to find that 0 is equal to, there's only one mass flow rate, times H in minus H out, oops, minus V out squared over 2. I can divide both sides by the mass flow rate, so I don't really care what it is. And here I find that V out squared over 2 is equal to H in minus H out. Right? And now here, because it's constant specific heat, is going to be Cp times T in is T4 minus T5. Yep. And then, right, so now I got to think now about units, right? Because anytime this sticks around, I got to think about units. So, units here, this is going to be in kilojoules per, so this is kilojoules per kilogram Kelvin multiplied by delta T in Kelvin. So this is what we expect, kilojoules per kilogram. Same as if we looked it up in the textbook. Right? This is in meters squared per second squared, which is the same as meters per second squared times meters. But meters per second squared is an acceleration, right? And Newton told us that force is equal to mass times acceleration. So acceleration is equal to force over mass, right? Acceleration is in meters per second squared. Force over mass is going to be newtons per kilogram. So this is newtons per kilogram times meters, right? Which is joules per kilogram, right? Not kilojoules per kilogram. So now I'm going to have to take this number here and multiply by 1 kilojoule per 1,000 joules. So if I wanted an equation just for the velocity, this would be that V out is equal to 2,000, right? Because this would be 2 times 1,000, right? But we move it up. This is in joules per kilojoule times Cp, which is in kilojoules per kilogram Kelvin, times my temperature, which is going to be T4 minus T5. That's in Kelvin. The Kelvins here are going to cancel. This all, though, is to the power of 1 over 2, right? Because I got to take the square root there. The kilojoules cancel, right? This is joules per kilogram, but we just saw that joules per kilogram is the same thing as, so this is, we know from above, right, that when we had joules per kilogram, that's the same thing as meters squared per second squared. So this is going to be all of this, and the units inside here are meters squared per second squared, but we'll take the root of that, and that'll give us meters per second. So the units here work out. I know this constant, I know Cp, I don't know T4 or T5. But if I did, then I can find this velocity. Right, so here's my answer for C. At least my symbolic answer. And that's great. But now we got to do this first thing that it told us to do, right? Which is, fix all the states. And again, if this was an exam problem, I would expect you to know how to fix any one of these states, but probably I would not expect you to do all of them, right? But like so many of these different problems, we're going to just march through the states. Oh, it's kind of hilarious because, like I said, I grew up in Canada, right? So my knowledge of American states is pretty terrible. So my daughters, are going through school and they got this app, right? And it shows pictures of the different states, but not scaled to the right size. And my eldest daughter is super good at it. She gets, maybe 2 wrong, right? And I haven't even tried it, but I'm pretty sure. I was talking to my brother, and I know for sure there's 10 or 12 that I could get, right? But after that, I don't know. There's a lot of unknowns there. So I got a lot of studying to do. I was planning to take, because I can go for my citizenship test, and And I was planning on doing it this summer, but this summer is now almost over, so I got to make time. State A. So ultimately, because we're doing this as constant specific heat, what we want to know is we want to know the temperature and the pressure of all the different states. And the beautiful thing about state A is we have both the temperature and the pressure. Here, why don't I do this? I'll pull this down. T at state A is 230 Kelvin. P at state A is 26 kilopascals. From state 1 to state 2. I ask myself, because it's air is the working fluid, is delta S equal to 0? And the answer is yes. Right? Now, normally what that would mean is that I could say, and this is definitely true, so for this particular state, I can write down my isentropic equation, which is that if I want to find T1 over TA, that's going to be equal to P1 over PA to the power of K minus 1 over K, or that T1 is equal to TA times P1 over PA to the power of K minus 1 over K. The awesome thing here is I know TA, I know PA, and I know K. The bad news, though, is I don't know T1 and I don't know PA. If I was doing this really quickly and it told me that the compressor pressure ratio was whatever it was, 12 or something, but here we're not going through the compressor. We're just going through the diffuser. So that means I can't use this equation yet because I have two unknowns. So what do? If I'm ever lost in thermodynamics class, it's always a good idea to write down the first law, right? And now we're going through the diffuser, right? These problems get a little tedious because we end up writing down the first law many times. But I think it's very much worth your while on an exam to write down the first law. Do not skip this step because this is the step where you're demonstrating your understanding, which, remember, is your job on an exam. H in plus V in squared over 2 plus GZ in minus the sum M dot out, H out plus V out squared over 2 plus GZ out. Now, we already did this for the nozzle, and it's going to be very similar. Steady state, adiabatic, passive, one inlet, one outlet, no potential energy change. But it's the state that doesn't touch the rest of the engine that gets neglected for the kinetic energy. And if my think and render here, right? So here it's the inlet state that's open to the air that's not touching the rest of the engine, right? So it's my inlet kinetic energy that survives. That's the energy we're trying to harvest, right? So here, this means that 0 is equal to m dot, only one mass flow rate in the problem, HA plus VA squared over, we've already done the units, so we know that this is over 2,000. Minus H out. We can cancel the mass flow rate. And here I can see that H out is going to be, well, because it's constant specific heat, let's leave it like this for a second. Right? So this is, if I clean this up a little bit, it's going to be 0 is equal to HA minus H1. I dislike how it does that sometimes. I don't know what it is, if it's something on my hand or something that triggers the HA minus H1 plus VA squared over 2,000. So I know the units are correct, right? Because I did that already. But because this is, I'm doing constant specific heat here, this means that 0 is equal to Cp times Ta minus T1 plus Va squared over 2000. Or I can get T1 minus Ta is equal to Va squared over 2000 times 1 over Cp, or that T1 is equal to Ta plus Va squared over 2000 times 1 over Cp. So now I want to put this into my calculator. So this is going to become Ta, we know, is 230 Kelvin. Va is going to be the velocity of the jet, which was 220 meters per second. Meters squared per second squared divided by 2000 times Cp is 1 kilojoule per kilogram Kelvin. Okay, let's see what we get here. I have a calculator somewhere. 220 squared divided by 2000 divided by 1. So this is 230 Kelvin plus, this is 24.2. We know that this meters squared per second squared is the same thing as joules per kilogram. And this 2000, right? So this was really 2 times, so this 2000, right, it's tricky because now it's in the denominator, right? So this was 1,000 joules goes on the bottom and kilojoules goes on the top, right? So this is joules per kilojoule. And then here we have, I'm just going to put this numerator in the denominator of the denominator is going to go up to the numerator. Kilograms Kelvin per kilojoule, right? So these joules are in the numerator of the numerator, and the numerator of the denominator cancel, right? Here I have kilojoules in the denominator of the denominator, but joules in the numerator of the denominator, which is not easy to say. These kilograms cancel, so I get, this is good, right? So I can add this up. This whole ugly term here is in degrees Kelvin. So this is going to be 24.2 plus 230 is 254.2 Kelvin. This is T1. But I don't just need the temperature, I need the temperature and the pressure. Right? So actually now this equation I got to rearrange because when I wrote it down that way, I was thinking I was going to use it to find the temperature, but really what I need to do is find the pressure, right? So if I manipulate this further, this becomes T1 over TA to the power of, I invert the exponent, K over K minus 1 is equal to P1 over PA, right? Or P1 is equal to PA times T1 over TA to the power of K over K minus 1. Right? Or P1 is equal to PA, they told me PA was 26 kilopascals, times T1 is 254.2 Kelvin. The kelvins are going to cancel because both temperatures are in Kelvin, divided by 230 to the power of K, which is 1.4, over K minus 1, which is 0.4. So I'm going to do this all in my calculator, where hopefully I don't mess it up. 254.2 divided by 230 to the power of 1.4 divided by 0.4 times 26. So here I get 36.9 kilopascals. So I think this makes sense, because what the diffuser is doing is taking kinetic energy in the fluid and turning it into enthalpy, right? So the temperature went up, right, from 230 to 254, and the pressure went up too, which makes sense if we look at our TS diagrams, because remember, this is a constant pressure at from A to 5, because they both touch the environment, and this pressure here at 1 is not the same pressure at 4, but the pressure did go up. So I don't know if the numbers are right, but at least conceptually, you know, my units are correct, and I get the right direction of change. So now I'm going to go from 1 to 2. This is an isentropic compressor, right? Which means that delta S is equal to 0. Which means that I can say T2 over T1 is equal to P2 over P1 to the power of K minus 1 over K. I can now find P2. So P2 is equal to P1 times R. And here they told us the compression ratio was 11. So if I take this 39 or 36.9 times 11, I get 405.9 kilopascals. Right, but P2, really P2 over P1 is just 11, right? So this is R, which is equal to 11. So T2 is equal to T1 times R to the power of K minus 1 over K, or T1 was equal to 254.2 Kelvin times 11 to the power of 0.4 over 1.4. 11 to the power of 0.4 divided by 1.4. That's about 2 times 254.2. This means that now we know the pressure at 2 and the temperature at 2 still going up, which makes sense because we're going up to the turbine. So the temperature should be going up until we get to the turbine. 504.3 Kelvin. Does that part make sense? So that's going through an ideal compressor. The tricky thing here is we knew that this was ideal, so we could use this isentropic relationship because the working fluid is gas, or an ideal gas, and we knew R, then we could find T2. I think it might be too confusing if I, in parallel, try to do this as a variable specific heat problem. But if you go to the notes here, so let's say as you're going through from 1 to 2, right, then you can see we get the temperature here and the pressure, right? So here in the notes, I do it in parallel as variable and constant specific heat. So you can still see how that's done. Now, as I go from state 2 to state 3, this is heat in. Because there's no friction losses, that means that P3 is equal to P2, which in this case is 405.9 kilopascals. And I don't have to do anything to figure out T3. It could be if they told me Q dot in, then I could use that to find T3. But I don't have to do that because they told me T3 is 1400. So state 3 is done. My two favorite states, and this will almost always happen in turbojet engines, is they will tell you state 1, which is as you start to go up to the turbine. And then once you get to the inlet of the turbine, they generally tell you that temperature too. And if you're working with an ideal gas, states where they tell you the temperature are great because you're pretty much already done with that state. Right now, if you're keeping track, we won't go through this yet because I'll just do it at the end. But if I wanted to know, right, when we first set up our, it really doesn't like it once I get all these pen strokes in here. Right, so now we know m dot was given, CP was given, and we know T3, and we found T2. So now we're able to find Q dot in. Right, so that's half the battle here. Right, so this is the way I think about turbojets, is to break it down into two halves. One where you're going up to the turbine inlet, and then one where you're going down to the exit of the nozzle. So we're basically halfway through. But now we got to go from state 3 to state 4. This is the turbine. Two things here are important in the turbine, right? One is that delta S is equal to 0, at least if it's an isentropic turbine, which in this problem it's all isentropic. But the second thing is that the back work ratio is equal to 1, right? So that means if when I do the first law, on the turbine and the compressor, they're both going to be steady state, one in and out, no kinetic energy change, no potential energy change, right? And they're both going to be adiabatic. So that means that W dot is going to be M dot times H in minus H out. And if the back work ratio is 1, that means the magnitude of the compressor power is equal to the magnitude of the turbine power, right? Or M dot, the compressor is H1 minus H2. They're equal but opposite, so there's going to be negative M dot. The turbine goes from state 3 to state 4, H3 minus H4. The mass flow rates are going to cancel. But we're doing this problem as constant specific heat. So this is going to be Cp times T1 minus T2 is equal to negative Cp times T3 minus T4. Same specific heat because we're saying it's constant throughout the whole problem. Right? The thing that I'm trying to solve for here is T4. So now T4 is going to be equal to T2. Right? So I got to move this over to the other side. And this part over here. So T2 minus T1 minus T3. T2 is 504.3 minus T2. No, sorry. Yeah, minus T1 was 254.2. Oh, you know, I messed this up. This is why you don't skip steps. I'm going to erase this. Because we're going to get a negative number if we do that, because T3 is the biggest number. So instead, so I don't mess it up, I'll multiply out the brackets. T1 minus T2 is equal to, I got to multiply this by, right, so this is going to be T4, because I multiply this by -1, minus T3. Or T4 is going to be T1 minus T2 plus T3. So T1 is, what do we say? 254.2 minus T2 is 504.3. These are all in Kelvin, so I'm not super worried about the units. 1400 is T3. $254.2 minus 504.3 plus 1400. This is 1,149.9 Kelvin. But temperature is not the only thing we need. We need P4. It's really important to remember that P4 is not equal to P1. If this was a Brayton cycle, people would say P4 is equal to P1, and then they would use an equation like this isentropic equation to find T4. But you can't do it that way, right? Because those pressures are not equal. P1 is not equal to P4. So we have to find P4, right? But we can still use the fact that delta S is equal to 0, because we haven't used that equation yet, right? So here we know that T4 over T3 is equal to P4 over P3 to the power of K minus 1 over K, or that T4 over T3 to the power of K over K minus 1 is equal to P4 over P3, or that P3 is equal to, P4 is equal to P3 times T4 over T3 to the power of K over K minus 1. P3 we know is the same as P2, which is 405.9 kilopascals. We're expecting, as we go through the turbine, this pressure to go down. T4 we just found as 1,149.9 divided by T3, which was 1,400, to the power of K, which is 1.4 over K minus 1, which is 0.4. If I put that all into my calculator, I get 1149.9 divided by 1,400 to the power of 1.4 divided by 0.4. 0.5, so that's good. It's going to come down, times 405.9. And here we get 203.8 kilopascals as P4. And that's good. Now we have T4 and P4. Now we got to go from state 4 to state 5, which is the nozzle. The nozzle, we're also going to assume delta S is equal to 0. We have also done the first law on the nozzle. And the first law told us, right, that was the the equation we did right here up at the top when we were doing our symbolic solutions. So it told us that V out squared over 2000 is equal to Cp times T4 minus T5. So V5 squared over 2000 is equal to Cp T4 minus T5. We're doing okay here in that we know Cp, now we know T4. If we knew T5, then we could solve for V5, right? And the way we get T5 is we know that this is an isentropic process. So it's really important to know where these isentropic processes are. So because it's an isentropic process, that means that T5 over T4 is equal to P5 over P4 to the power of K minus 1 over K. P5 is the same as P1 or PA, which I believe was 23 kilopascals. 26 kilopascals. So here, T5 is equal to T4 times P5 over P4, K minus 1 over K, or T5 is equal to T4, which is 1149.9 Kelvin. P5, which I just said, which I think is 26 kilopascals, divided by P4, which we found to be 203.8 kilopascals. The units cancel. As long as they're the same units, like, I couldn't do pascals in kilopascals, but because they're both kilopascals, that cancels. This is K minus 1, which is 0.4, over K, which is 1.4. This is T5. This is going to be, I get 26 divided by 203.8 to the power of 0.4 divided by 1.4, all times 1149.9. So again, we're cutting this temperature down, which makes sense. This is 638.5 Kelvin. So now I fixed all the states. Right, so because we fixed all the states, now we, so here we have T3 and T2. I had an equation for V out. Now I know T4 and T5. I'm going to go back to the notes to show you what the actual numbers are here. So V5, we're always talking about the moving frame of reference here. And this is about 1,010 meters per second. Right? T5 we have here. The other piece we wanted to know was the heat transfer rate, which we solved here. And you can see, even in this problem, where we're getting big temperature swings, we still get pretty good agreement with the constant specific heat and variable specific heat. Although here, 11%, that's still, it's a sizable number, but it's still giving you qualitatively good information, right? Depending on what these temperatures in. If you make some kind of a change in your system, you can see, will that increase my heat transfer rate or reduce it? But you can see that if you really want, because the temperature differences here tend to be large, right? Using the tables gives you a better number. And this is the more accurate number, right? With the variable specific heat or the air standard analysis, right? And here you can see for the velocity, it's again, a reasonable difference here. So that's how you do the problem of the turbojet. Does anybody have questions? So I think that the big things here are you need to get your units right when you talk about those kinetic energy terms. You need to remember that the back work ratio is 1, so that when you're solving the exit of the turbine power, you need to say that the back work ratio is 1 of the real components. And then you find the pressure drop across the turbine by using that isentropic relationship. So it's going through the turbine is a little bit backwards compared to how we would do it in a Brayton cycle. So we have a decision to make now, because we can either cut the lecture short and then deal with refrigeration systems and heat pumps next class, or we can push through and do refrigeration and heat pumps now and then have all of next class for review. So I don't know if anybody has a preference in the chat. So if you do have a preference, please let me know. I would say usually, so there's the question in the chat is how many review classes does the normal class usually get? It sort of depends. I would say either 3 or 4. The way we're going to do review, so I have maybe like a 20-minute review presentation, right? So we can go over that. And then what I'll get you to do, which we'll talk about next anyway, is I'll sort of get you to elect what cycles we want to do in the review, and I'll ask people to pick, or scour the internet or look through the textbook, try to find as complicated a problem as you can, or at least some version of a problem there, and then if you can bring it to class, you can show it to me in real time, and then you can see me do a problem when I haven't really prepared for it. So I would say usually a class gets somewhere, when I teach it, somewhere between 3 and 4 review periods probably. So there are 5 cycles basically that we learn. You could maybe say auto and diesel makes this 6, right? Or you could say refrigeration and heat pumps make it 7, but refrigeration and heat pumps we'll see are basically the same thing. So that was a long-winded answer. So, right? And if you think about these lectures, each lecture here in the evening class is supposed to be between 3 and 4 lectures. So, it's up to you guys how we do it. I think it'll work either way. Okay, I think that seems reasonable. We do have time, so to try to go through and do it. And I think the nice thing about these refrigeration problems is that I think they're the most straightforward of. That's good. You got nothing else to do. They're the most straightforward of the problems. I think of the different cycles. So we can do that. But maybe before we go to break here, we can take a poll of the people here. So I think then maybe we can try to do. Well, let's prepare for 2. We might only get 1 done, but of these cycles, what cycles do you think are the hardest ones we've done so far? Or which ones do you want to spend time reviewing? Maybe we'll pick 1 for next class, and then we'll try to do maybe 3 on the next class after that. This is what happens when it's a small group, because the next question is going to be, if you write something down, then I'm going to ask you to find a problem. But it doesn't take too long to find a problem, right? So I think that in some ways, I think diesel is harder than auto, because you have this constant pressure term, which means that there's work in 3 places. I think of the Rankine cycle problems, the hardest ones are regeneration, but maybe you can find a problem that has regeneration and reheat in it, right? And that gets pretty complicated. Brayton, the hardest Brayton cycle is the one that's got all of these different components in it. Turbojets are hard because we got this kinetic energy term. They're harder if the turbine is a real turbine. So I do have an example prepped for that, so we can do that one. And then I find that people tend generally not to review heat pumps and refrigerators because they're the last one we do, and I think they tend to be fairly straightforward. And the reason that I ask students to do these is because I don't really feel comfortable picking the review problems myself, because I know the problems that are going to be on the exam. So maybe since we don't have a volunteer yet, what we can do is next class, I can bring a general problem that's a turbojet problem that has a real turbine and a real compressor. Right? But I'm going to need someone else to volunteer to either find a diesel problem. All diesel problems are more or less the same, but the inputs could be different. A very complicated Rankine cycle, so one that probably has reheat regeneration. Maybe it's got 4 turbines or something in it. Maybe it's got open and closed feed water heaters, right? So I would say pick one of those 2. So can someone please volunteer to bring us one of those problems? I think basically, because there's 5 students in the class, everyone's going to have to bring one problem in for the review. So if you volunteer to bring one in now, then you're done. Thanks, Jules. Which one? You want to try to find a Rankine cycle problem or a diesel cycle problem? Perfect. So the more complicated you get, the more you get to see me square. So, and I think it's better because you pick one that's really tough, right? Then it sort of helps alleviate this idea that, you might open the test and see something you've never seen before. So I appreciate you do that. Yeah, and Vidra, if you can find a diesel cycle problem, that's great, right? So, right, so then we'll be good, right? And then we, and maybe we'll even be able to do all 3 of those problems next class, but at least 2 of them. But if you find both of those problems, then we'll be good. So maybe we can take a break for 5 minutes here. So we'll go to 8:25. This one just because it's planes, right? Like, I wouldn't want to be this tightrope guy if it's real. So we'll break till 8:25, and I will see you then. Thanks, everybody. Welcome back, everybody. Let's see, it looks like Jules just emailed me or sent a picture in the chat. Oh, good. Nice. So here we see one that's really complicated, right? So this will be good. So we come out, so we split out of this turbine here, right? So this will be good. It'll be challenging. So challenging is good. Right? So we will work on that next class, right? And oops. Apparently it helps if you're not muted. I see the problem that Jules found there. It looks pretty complicated. So, that'll be good. It'll keep me on my toes. And it's nice to see, I hope it's nice to see me struggle, because then that gives you some idea that that you can do these problems like you've never seen before, as long as you follow the process that we talk about, right? So we have some volunteers here for questions, so that's good, right? If you want to see some other cases, so this was from, I don't remember what summer it was from. Oh, there you go, last summer. So these are the problems that people brought in last summer. So if you want to spend, these were kind of 1 hour lectures, right? So this was a complicated Brayton cycle, a turbojet problem with an afterburner, a Rankine problem that had open feed water heater, closed feed water heater with regeneration and reheat, and then sort of a general discussion of internal combustion engines. So you can check those out too if you're looking for other kind of complicated problems that might be worth looking at. Right? So what we're going to look at today, or now I guess, right, is this idea of refrigeration and heat pumps. Right? So it may be, depending on where you live, that you have some familiarity with heat pumps and how they work, and how that they can be essentially air conditioners in the summer and the equivalent of a furnace in the winter, right? So it's kind of the same piece of equipment, right? So when we do these problems, they're also going to be open system problems, right? So as we do these open system analyses, right, we need to know what the control volume is. We're going to do conservation of mass, right? We're going to do conservation of energy. And then sometimes we also have to do the second law too, right? So you might be asked, find the entropy generation rate, right? But another way we thought about the second law, right, was from these Kelvin and Planck statements, right? So Kelvin and Planck, they told us, this was about heat engines. And they said, yeah, you can make a heat engine, something that takes heat in from the hot place and turns that heat into work, but it can't turn all the heat into the work because you got to cool the engine down, right? Right, and that's like the genesis of thermodynamics, right? So, we're turning heat into work, right? So for me, when I think about this, I think about the steam engine, right? So the Industrial Revolution, and sort of in my mind, that starts with the steam engine, right? I put this picture in because I think it looks cool, right? But there's another problem at a similar time, right? And that's that, it sure would be nice to be able to preserve food, right? And there's all kinds of different ways that we can preserve food, right? One is we can salt meat, right? So if you think about, the age of sail in pirates, right? So they're, a lot of salt pork they talk about a lot, because it was something that they could bring on ships and keep for a while, right? You could smoke meat. Maybe I told you this, but my brother lived in Texas for a little bit, so he sort of got indoctrinated into Texas barbecue, right? So usually when we go down there, it's great. He's got briskets or ribs or something going, right? And my grandparents, they in their house, which is an older house, obviously because they're older, right? They had a cold cellar, right? So that was an uninsulated room that was basically open. Well, not open, but didn't have insulation, right? So it was cold because the earth is cold as you dig down far enough, right? Right? So, this has obviously never happened, right? But somebody like Clausius comes around, right? And he looks at that cold cellar and he says something like, well, can I make a machine that keeps some volume of air cold, right? Can I make a refrigerator, right? And Clausius, when they look at the second law, right, thinks, okay, well, now we're not taking heat in from the hot place. We're pushing heat from the cold place to the hot place. And we can do that, but we can't do that and generate power. In order to do this, we have to be putting power in order to get it to work, right? So that's why you got to plug your fridge into the wall, right? Or you plug an air conditioner into the wall. Right? Because these things require power. Now, when we talk about refrigeration cycles, they're essentially Rankine cycles, but they run in reverse, right? So the cold part's at the bottom, the hot part's at the top, and we're going the wrong way around the cycle, and we go into the compressor is on sort of the turbine side, right? So when we have the vapor, we're not going through a turbine, we're going through a compressor. And instead of a pump, or instead of a turbine on the liquid side, we have this valve instead, right? So what this does, what makes a refrigerator is your perspective. So if the thing that you're interested in is removing heat from the cold side because you're trying to keep the air in your freezer or your refrigerator cold, then you're thinking about a refrigerator. But a heat pump is the same thing, just now your perspective is on the hot side and you're more interested in that heat rate coming out of the condenser. Now, refrigeration units run with refrigerants, right? And refrigerants, this is why we're friends with chemical engineers. They make these chemicals that are bouncing back and forth across the vapor dome, right? So they boil and condense at lowish temperatures, right? So much different than water. So we'll see that this is not generally how you run these cycles, but we could think about the condenser. What if the condenser went just from saturated vapor to saturated liquid, right? Then it would go from state 2 to state 3 over here, right? If it was an ideal compressor, right, then you would have a vertical line up from state 1 to state 2s. The expansion valve is a little bit different than if it was a turbine. So the expansion valve is not isentropic, right? So it's not that the entropy stays the same. We'll see the expansion valve. And if you remember from when we first were talking about sort of the Lego bricks that we're going to use for open systems, we talked about how expansion valves end up being isenthalpic, or H doesn't change. And because it's not isentropic, I'm very careful to sort of exaggerate the slope here so that it's not, doesn't look like a vertical line. And then if we were all under the vapor dome, then the evaporator would go from left to right. But probably you want to come out of the expansion valve as a liquid and then boil it over here. But if everything was under the vapor dome, it would look like this. You would be putting work in the compressor, rejecting heat on the hot side of the system, potentially getting work out of the valve if it was acting like a turbine, and putting heat in at the evaporator. So here, it's sort of like a Rankine cycle in that we have a vapor dome that we're bouncing back and forth across, but we're going kind of the wrong way around the cycle, and all our arrows are pointing in the opposite way. So I think of heat pumps and refrigeration cycles as Rankine cycles run in reverse, right? How do we characterize the cycle, right? So it's still energy benefit over energy cost, but in a refrigeration cycle, the energy benefit isn't the net power. The energy benefit is, because it's a refrigerator, it's the heat that we remove from the cold side. Whether that's the air in your refrigerator, or if it's an air conditioning unit, it's just the air in your house or the air in your car, right? But then the energy cost is the net power that you're putting in. In order to run this system, you're not burning, well, I guess you could run your compressor on diesel or something, right? But typically these things are plugged into the wall, right? So you're running on electrical power. You're putting power in. For each component, we can do the first law, and this looks very similar to the Rankine cycle. All the components are steady state. All the components are one inlet and one outlet. There's no kinetic energy changes, no potential energy changes. All the components, at least for now, we're going to say are adiabatic or passive, just like we would in the Rankine cycle. And we're going to say no friction losses and no heat losses in the lines. Right? So constant pressure if we're adding or removing heat, and we're not doing first law analyses on the lines so that the state at the outlet of one component is equal to the same state at the inlet of the next component in line. So then we're going to get very similar equations that we would get for a Rankine cycle, or even for a Brayton cycle, really, right? Is that if we're trying to find power, it's m dot times h in minus h out, If we're trying to find a heat rate, it's m dot times h out minus h in. But what the further assumption that we make about the valve, right, is that it's isenthalpic, right? So it's not isentropic where delta S doesn't change. It's isenthalpic that the enthalpy stays the same. So there's no change in H. So that means that the valve is really boring. Nothing happens in the valve except a pressure change, right? Because the pressure changes, then that valve power goes to 0, right? So there's really only 3 components that we care about, right? And depending on, if it's a refrigeration cycle, I really only care about the heat that we're taking out of the cold place, and my net power is just my compressor power, right? So because we're talking about a refrigeration unit here, it's Q dot removed from the cold side that I care about, right? You do have to be careful with your subscripts. I like to think about this as Q dot hot and Q dot cold, because then I don't have to remember what the evaporator and the condenser are doing, right? Because it's a little counterintuitive what they're doing in this case. But if I just wrote Q dot C here, then I might get confused, because it could be Q dot cold, which is the evaporator side, or it could be Q dot of the condenser, which is the hot side. So be careful with your subscripts when you talk about heat pumps and refrigeration units. So now if we're trying to characterize this cycle, we use the Greek letter beta, but I remember that because it looks kind of like an R for a refrigeration unit, right? If you squint anyway. But if not, you can just call it a COP, or coefficient of performance, right? It's going to be the magnitude of the heat rate removed from the cold side divided by the net power, which is really just going to be the compressor power, right? So the first law will tell you this is H1 minus H4 divided by H1 minus H2. But then you take the magnitudes, right? Now we can always compare this to the Carnot or ideal refrigeration cycle, which is going to be just T cold over T hot minus T cold. Heat pumps are exactly the same cycle, right? The only thing that's different about the heat pump is the energy benefit. What's your perspective? In a heat pump, this is sort of like a furnace. The purpose here is to heat up the place that's already hotter than the place you're taking the heat from, right? So here it's like you're taking heat from the cold place and pushing it into the hot place for the benefit of heating up the hot place. So it's really the exact same system. It's just you care about a different part, or you care about the energy transaction that's happening in a different component. So we get the exact same equations. The valve still has 0 power. The compressor power is still m dot times h in minus h out. The heat rates are still m dot times h out minus h in. But now what we care about is the heat rate on the hot side, right, which is the condenser side. Again, we talk about coefficient of performance. Here we use the Greek letter gamma. I don't know why, right? But again, if you forget, you can just put COP. That's fine. It's still going to be the energy benefit divided by the energy cost, right? But now the energy benefit of a heat pump is the heat rate put into the hot side. The cost is still the net power, right? So from those equations above, you can get this as a function of enthalpies because the mass flow rates cancel out. And then we can always check, and for something to be possible, we know that the actual coefficient of performance has to be less than the maximum coefficient of performance. I didn't say this for the for beta max, right? That this temperature especially, you need it to be in Kelvin and Rankine. But anytime I'm doing those Carnot calculations, I always use absolute temperatures, because you won't get it wrong if you use absolute temperatures. In that way, I just don't have to think about it. I just automatically go to absolute temperatures. Right, so now heat pumps and refrigerators, I get my equations, right? And they're the same, right? The only difference is which heat rate I care about, right? So for a refrigerator, I care about the cold side heat rate, and for a heat pump, I care about the hot side heat rate. Now, I'm at the point in thermodynamics, right, where I say, what's the fluid? Because now I've got my equations, right? So if I'm thinking about this, the energy benefit and the energy cost is going to be some heat rate is the benefit divided by the compressor power, which is the same as the net power here, right? They're all open systems, so I get these equations, right? But then what's the fluid? It's going to be some kind of a refrigerant, and we treat those refrigerants in the same way that we treat what's it called? Water, right? Because it's going back and forth across the vapor dome. So it's not like an ideal gas. It's like water. Right? So if it's the fluid is a refrigerant, so I got to fix the states the way I would fix states in a refrigerant. So normally we'd look this up in tables, right? So just like water, we'd go to like the R134A tables instead of the water tables. But we use them in the same way, where if it's under the vapor dome, we're trying to find quality, right? And if we have a temperature and pressure, we're trying to think, well, is that going to be a liquid, or is it going to be a superheated vapor? We're going to talk about today, which is kind of a practical thing, is how can we fix the states using a pH diagram, which is basically a scale version of a vapor dome. And if you want to do these calculations quickly, then you can do them graphically, which is what we're going to try to go through for the rest of today. Right? Ideal compressors, we're going to find delta H when the delta S is equal to 0. And then we go to the real compressor, so we need to use the compressor efficiency, which is like the pump efficiency, where the ideal power goes on top because it's a cost to the system. Right? The isenthalpic valve is nice because delta H is 0. So once you know H3, you also know H4 because that's what isenthalpic valves are, right? So this is a pH or a pressure versus enthalpy diagram. Sometimes people call them SUVA charts, right? And it looks kind of intimidating when you look at it. This is like if you take Thermo 2, you might get faced with another intimidating graph called a psychrometric chart, which kind of acknowledges the fact that air isn't just air, that it's got water vapor in it too. But we don't worry about that in Thermo 1, right? So this is a way to graphically fix the states, right? It's just a scale diagram of a vapor dome for, in this case, refrigerant 134A. Right? So there's a couple of things about these diagrams that are important, right? So it's pressure versus specific enthalpy, although they just call it enthalpy. They never say the word specific on this diagram anywhere, but all of the values are intensive properties, so they're specific. If it's volume, it really means specific volume. They're kind of cool because you can get most of the information that you'd get off the charts and tables. You don't have to do any interpolation, but you lose some accuracy because you're just solving these things graphically, right? Like I said, they don't say specific in front of any of the variables, but anything that could have a specific in front of it does, right? So it says pressure, it means absolute pressure. It says enthalpy, but it means specific enthalpy. Temperature and quality are always intensive. It says entropy, but it means specific entropy, right? And it says volume, but it means specific volume. Right? So how do I read this graph? Pressure and enthalpy are the easiest things to read on this graph. Pressure is horizontal lines. The tricky thing here is this is a log scale, right? So you notice the difference between 0.01 and 0.02, right, is different than, well, I guess 2 to 4 is twice that, right? But 2 to 4 and 4 to 6 is different values, right? So again, you're estimating these things. You're looking for the line that you know, so the pressure that you know. This is pressure in megapascals, but it's got pressure in bar on the other side, so the other vertical axis. If you're trying to measure specific enthalpy, right, because when we're trying to solve the first law, it's the H values that we're interested in, right? Then ultimately, when we find our points, we'll just drop a vertical line down and then estimate what the values for H is. Constant temperature lines go down until they hit the vapor dome, and then they go across the vapor dome, and then they go down. So really it's down and to the right, I guess. But when you're in the liquid region, then it looks pretty vertically down. One thing you do have to be careful of, because although I'll give you a better quality version of the better image than this one, I always look where 0 is, because sometimes if I'm going too quickly, 10 and negative 10, it's a little sometimes tough to see where this negative is, right? Because these temperatures are not absolute temperatures, they're relative temperatures, right? So in this case, Celsius, but if it was imperial, it would be in Fahrenheit. You have quality values under the vapor dome. So this is quality 0, 0.1, 0.2, 0.3, etc., all the way to 1. Obviously, you only get quality under the vapor dome. Specific entropy lines, I think, are sort of the hardest ones to read. So the values are down here, right? And these lines, the slope sort of changes as you move. They start pretty vertical on the left, but then they tilt more and more as you go left to right. Specific volume lines are also a little bit weird in that they sort of have this, they look like hair sticking up on top of a mountain or long grass or something in the wind, right? So they have this kind of funny shape to them, right? If you're looking for volume lines are given up this side here, but then when they run out of room, then they switch in here and they just give you at the top there. So in order to fix a state, as long as it's not an ideal gas, we need two independent intensive properties. The cool thing about these graphs is that every intensive property is essentially a line, right? So if you have a value for quality, well, then you can draw a line, right? And if you have a value for temperature, you can draw a line. And where those two independent intensive properties intersect, they will intersect at a line. If you have two, or at a point, right? So if, that's your state point. But if you have dependent properties, they'll intersect, but not at a point, at a line, right? So then you wouldn't be able to fix the state. As long as you know that point, then you can drop a vertical line down and you can tell me the enthalpy, right? Or you can look where it is in relation to all the other lines on the chart and give me any other property value, right? So here's just a quick example of how to use this chart, right? So here we have an evaporator. We're going in at state 1 at 5 bar, or 500 kilopascals, and we have a quality of 0.2. And then what we do is we add some heat per mass flux, or mass flow, sorry. And then we come out at the same pressure, but we're at 20 degrees, right? So we've boiled some water. So what this problem asks us to do is find the heat rate per unit mass flowing through this evaporator, right? So we're going to draw our control volume. That's the first thing we do for open systems, right? We do conservation of mass. It's pretty trivial in this case, right? Because it's going to be, we're going to assume that it's at steady state, that it's one inlet, one outlet, so there's only one mass flow rate. So the mass flow rate at the inlet is equal to the mass flow rate at the outlet. The first law here, this is a metric problem, so I should get rid of all these GCs, but I'm going to cancel those terms anyway. So we're going to say it's at steady state, one inlet, one outlet, no kinetic energy changes, no potential energy changes, and it's passive because we're trying to solve for heat rate. No friction losses, so the pressure stayed the same, right? And no heat losses in the lines, although here we don't really care about the lines because we're only looking at one component. So we're going to get the equation that we usually get, right? Is that Q dot is equal to M dot times H out minus H in. And we're expecting the heat rate to be positive here, right? So here, Q dot over M dot is going to be H out minus H in, right? We don't know Q dot, right? So this is the classic thermodynamic problem in that, yeah, it's great, we have a symbolic solution, but I don't know any of these variables yet. But if I could fix the states, if I can find H out and H in, then I'd be able to find Q dot over M dot, which is what the problem asked me for. Right? So now let's go through and fix the state. Right, so here we know state 1 is 5 bar or 0.5 megapascals, and the quality is 20% or 0.2. And we know state 2 is the same pressure, but 20 degrees Celsius. So first let's find state 1. Right, so here's our pH diagram. Now you could, well, we'll talk about this in a second. Okay, so first, so I'm trying to locate lines that represent both of these properties. So the first one is 0.5 megapascals. So here's 0.1, 0.2, 0.4, and 0.6. But you see, 0.5 is not exactly halfway. It's a little closer to 0.6 than 0.4 because it's a log scale. Right, so I draw a horizontal line at 0.5 megapascals. And then I'm looking for quality under the vapor dome, 0, 0.1, oh, 0.2 is over here, right? So where those two lines intersect, that's where my state point is. Now I'm going to draw a vertical line down from there, and I'm going to estimate here, you know, it looks like it's a little bit more than 250, right? I guess I could get out a ruler and like say how many millimeters between here and here, and what, but I just eyeball this, right? The reason you're doing this is to get an answer quickly, but the sacrifice you're making is accuracy. So I'm going to say that that's maybe 260 kilojoules per kilogram. But if you look this up in the textbook, it's way different than that, right? 108.8. And that's not like a graphical measurement error because 108.8 is like way over here, right? So what's happening? Why is this so different, right? We got to remember that enthalpy is a little bit like pressure or temperature in that there's no real natural 0 point. You could put the 0 point or the datum anywhere you want, right? So what this means is that whoever made the tables in the textbook and whoever made these charts, they just picked different 0 values, right? But that doesn't really matter because the first law is always asking us for delta H, right? So the changes should be the same even though the individual values are different, right? So they're all offset from the same point, right? And it turns out the textbook values are always about 150 kilojoules per kilogram lower than the handbook values or the values on this chart, right? What this means is that you can never do a problem half in the textbook and half on this graph. You have to pick one of these two methods and stick with it till the end of the problem. If you get a long answer problem, or maybe even a multiple choice problem like this, I will give you potentially these pH diagrams, but then say, well, you can use the pH diagram or you can use the tables. If it were me, I would use the pH diagram because it's faster. And an exam is really a game where you're trying to maximize your points per minute, right? So I pick the faster method, right? Here we got pretty lucky. I wouldn't expect your error if you're graphically measuring it to be this close, right? But I just happened to pick a number that was turned out to be reasonably accurate. Right, now let's fix state 2. Right, so it's still 5 bar, but now it's 20 degrees. So I still have this same horizontal line at 0.5 megapascals or 5 bar. Right, but now I'm going to look for the 20 degree line. And if I mistakenly picked minus 20, right, then I'd think that they intersect over here. But, oh, I see zeros over here, and we're moving higher, right? And this one is positive 20. So see how it goes down, and it hits the saturated liquid line before it hits the 0.5 megapascal line? So that means that we actually went past the vapor dome and got to vapor, which makes sense because we started off with some liquid vapor mixture where it was mostly liquid, and we added heat, right? So this is an evaporator. Its job is to evaporate or boil the fluid, right? So now I'm on the other side of the vapor dome as a superheated vapor. Right? Again, I'm going to drop a vertical line down here. I'm going to say that that's maybe 412 kilojoules per kilogram, right? Or if you said 410, that's fine, or 415, or, you know, if you do it this way, what I want you to do is, so if you fix the states this way, I want you to submit your drawing when you're drawing these out, right? So so that I can look to see how you were fixing the states, right? And obviously, you won't be graded on accuracy, right? I mean, you'll have to show that you're doing it correctly, but but you'll show that that it's you're following the right process. Hello. So thanks for coming back in. Right, so we still see the same difference here. Yeah, it's okay. I mean, I think that's one of the banes of Zoom is that, so we just had a student who had some laptop issues, so they were out for a bit. So what I would suggest is that you either check out the posted notes or maybe one of the thermo shorts or something to sort of get up to speed with where we are. So so we looked at how to do these cycles, and then basically how do we fix the states when it's refrigerants. So you probably want to check out the notes for that, but we'll go through a problem right after we're done this too. So you'll probably get some sense of how to do that. Right, so we did the first law, and we found out that the heat rate over the mass flow rate is what we'd normally expect, H out minus H in, right? And now we fix the states two different ways, right? So here's where we get to check to see, did the graphical method, was it reasonable, right? So if it's reasonable, we should get about the same answer, right? So if I use this pH diagram, then here I got a value of delta H, or Q dot over M dot, is equal to about 152 kilojoules per kilogram. In this case, I got pretty lucky. I wouldn't expect your answers to be this accurate, right? Like having an error on the order of 10% is certainly not unheard of doing this, right? So I just picked reasonably good numbers here, right? But you can see you get basically the same answer, even though, like I said, these values for H out and H in are significantly different, right? But that's just because it's like you're taking delta H in Kelvin, or delta T in Kelvin and delta T in Celsius, and the change should still be the same, even if the individual values are different. So we can take a break. Although maybe it's better to just go through so that we don't finish late, right? So now we're going to try to go through a problem. So we did this, right? So again, we'll do some hard problems in the next two classes. But if you want to see some previous, problems that people brought in for these review sessions, you can do that from these videos, which I believe are on my courses. So if they're not there, you can find them on my YouTube channel. But if they're not there, let me know and I'll add those links, because it's possible that I didn't bring them around. Right, so heat pumps and refrigerators are the same thing. So we're going to do a heat pump example, and I'll go through. Let me just bring up the file here. We'll go through and we'll do that heat pump example. Here, where is it? Right, so here we have this heat pump, right? So that's important. It's important to know whether it's, if you see a heat pump here, you can automatically circle, well, the thing that I care about is this Q dot on the hot side, right? I have a bunch of information here about the different states. I'm asked to find the mass flow rate. I'm asked to find the compressor power and the efficiency of the compressor, as well as the coefficient of performance, which, because it's a heat pump, is gamma. Right? So the first thing that I'm going to do is I'm going to get symbolic solutions for all of these parts. Right? So anytime I'm trying to find a mass flow rate, there's really three different things that I can look at. Option one, if I can take this, I'm always going to do this one first. Right? This is going to be that m dot is equal to the area times the velocity divided by the specific volume, or maybe the volumetric flow rate divided by the specific volume. Option two, maybe I look for a component with more than one inlet or more than one outlet. Right? Option three, I look for some place where I know W dot or Q dot, for both of these, I'm going to do the first law. So in this case, I don't have any components with more than one inlet and more than one outlet. I don't know the area, the velocity, or the specific volume anywhere, so it's not that either. So I'm looking for, I don't know anywhere where I know W dot, because I got to find W dot, right? I guess I know here W dot is 0 through the valve, but that doesn't help me. But I do know that Q dot out is 60,000 BTU per hour. So here I know Q dot out. Right? So here I'm going to do the first law on the condenser. So I'm going to say that dE by dt is equal to Q dot minus W dot plus the sum of m dot in, H in, plus V in squared over 2GC, because it's imperial, although we'll see that it doesn't really matter because I'm just going to cancel it out. G over GC, Z in, minus the sum m dot out, H out, plus V out squared over 2GC, plus G over GC, Z out. For all my components, they're all going to be steady state. They're all going to be one inlet, one outlet. They're all going to neglect kinetic and potential energy changes. Now, for the condenser and evaporator, they're going to be passive. For the compressor, oops, I'll use a different color here. The compressor is going to be adiabatic. Right, so here, I guess this means that Q dot is going to be m dot times H out minus H in. This means that W dot of the compressor is going to be equal to m dot times H in minus H out. And then for the valve, it's going to be adiabatic and passive. So here we're going to find that delta H is equal to 0. So H3 is going to be equal to H4. So for the mass flow rate, right, the thing that I know is the heat rate. So I know the heat rate of the compressor, or of the, condenser, is equal to m dot times, this is H out minus H in, but remember we're going the wrong direction here. So this is going to be H3 minus H2, or that m dot is going to be Q dot over H3 minus H2. So that's my symbolic solution. Here I know H, but I don't know H3 or H2. Or I know Q dot, I'm sorry, but I don't know H3 or H2. So here we have a symbolic solution. Compressor power, we already have an equation for this. W dot of my compressor is equal to m dot times H in. I go into my compressor at state 1, come out at state 2, H1 minus H2. This I'm going to get from part A. I don't know H1 or H2, at least not yet. For my isentropic efficiency, or my efficiency of my compressor, I'm going to get, this is going to be power over power, but the compressor is a cost to the system, so the ideal compressor costs less than the real compressor. So this is going to be m dot times H1 minus H2S divided by m dot times H1 minus H2. Finally, I want my coefficient of performance, which is gamma. Because this is a heat pump, this is going to be Q dot of the hot side over W dot net. And we'll take the absolute value there. I always put the absolute values because W dot net is always in, right? So work in is negative. In this case, Q dot out of the hot side is also negative, right? So in this case, you don't need the absolute value signs. But for a refrigerator, it would be a negative number. And you're never going to go into like Home Depot or something and ask for something that has a coefficient of performance, which is like the SEER rating of, there's some conversion factor, I think. Right? You're never going to ask for something that has a negative value, right? So you always just take the absolute value there. So this is Q dot of the condenser divided by, this is just W dot of the compressor. I'll put the absolute value signs, but they end up both being negative. In this case, I know this. It's just given to me. And this is my answer for part B. So this is the nice thing about these refrigeration and heat pump cycles, is that they're pretty straightforward from the symbolic solution part, right? Because they're kind of like Rankine cycles, but generally less complicated, because you don't have the like, oh, and then we do reheat, and then we do regeneration, and then we do reheat and regeneration, and then we do it a bunch of different times with different, you know, so it's always pretty similar, right? And the equations stay basically the same, right? But now how do we fix the states? And I could draw this on the diagram, but I think instead we'll go through fixing the states graphically over here. So again, you can go through the notes, right, and see how we do all this, right? And I got the symbolic solutions down there. But first, or I guess now, let's go through and fix the states, right? So this is a cleaner version of this. And if you get it on an exam, you'll have a nicer version instead of the one that I had in the last part of the lecture. So the nice thing here is that for almost all the states, we have two intensive properties. I don't always know if temperature and pressure are independent, but I'll assume that they are here. But this gives me a fighting chance to fix all the states. The only one where we only know one piece of information is the isentropic outlet of the compressor. But there, I'm going to remember that it's isentropic, so that delta S from 1 to 2S is equal to 0, right? So let's kind of march through these and see if we can fix them, right? So there's a bunch of states at 200 psi. So that's kind of where I'm starting from, right? So we can see that state 2, state 2s, and state 3 are all at 200 psi. Again, we can use that to figure out how many pressures we're supposed to have. We can look at the maximum number of compressors, which is 1, and the maximum number of turbines, which is 0. So the max of those two things is 1, and then I add 1. So there should be 2 pressures here, right? So we know a bunch of these states are at 200 psi, but some of these states should be at some lower pressure too, right? So if I look at state 2, it's 180 degrees Fahrenheit. So that's this line here, right? And it's 200 psi, right? So I fixed state 2. I'm going to leave 2s for now. I know it's on somewhere on this 200 psi line, but I don't know where, right? But state 3, well, that's at 110 degrees Fahrenheit, right? So 110, here's 100, there's 120. So 110 is going to be somewhere in between those two. So I put this red line as 110 Fahrenheit, right? So that goes about there, right? Now, the next thing that I want to see, I see that state 1 and state 4 are both at 0 degrees Fahrenheit. So hopefully that's the next line that animates here, right? So 0 degrees Fahrenheit is here, right? And then I got a choice. I can do state 1 or state 4 next, right? So state 4, the thing I remember, as I move from state 3 to state 4, I'm going through that valve. And the valve is isenthalpic. It drops the pressure while keeping the enthalpy the same, right? That's its job. So state 4 is vertically under state 3. So that's cool. H3 is equal to H4. So I only really need to find 3 H values. 4, I guess, because I want the isentropic outlet too of the compressor, right? And then state 1, it tells me it's also at 0 Fahrenheit, but that it's at a quality of 1, right? And so quality goes 0.1, 0.2, all the way over to the saturated vapor line, which is quality of 1. And there's state 1. So now we have located state 1, 2, 3, and 4. But we still want 2s. And I find this to be the hardest of the states to graph here. So I'm going to say that state 1, I don't know, is a product. So here are the constant entropy lines, right? So there's one here and one here. And the slopes are a little different, but I'm going to say this state point 1 is about halfway between those two lines up here at 0 degrees Fahrenheit. So then I'm going to say that it's also halfway between these two lines over there, right? So I'm going to draw my constant entropy line and put it over here. So state 2s is approximately there. So now I've located all my state points. And in order to solve those symbolic equations, I need to find H values. Now, like we said before, you can't half do this problem in the textbook and half do it on the chart. You pick one or the other because they have different 0 points, right? So what we do now, I mean, you won't get to do this on yours, right? But I can get rid of all that other junk and just drop vertical lines down. So here, again, I'm not sure because I'm just graphically measuring it, but I'm going to say that that's about 45 BTU per pound mass, right? Straight down from state point 1, I'm going to say that's about 100 BTU per pound mass. It's a little tricky because they don't have tick marks out here. So they say 100, H is equal to 100 BTU per pound mass here, but I don't know where the tick mark's supposed to be. Is it centered on the number? I don't know. So I picked 100 there. I'm embracing the fact that it's not perfect, right? I'm gaining speed by doing this, or efficiency, but I'm losing accuracy, right? So here I'm going to say that's about 120, right? And then I drop one down here. I'm going to say that's about 133. And now I fixed all the states, right? And I did it significantly faster than if I was, doing a bunch of interpolation and looking stuff up in the textbook, right? So now we already did we can go through this again, right? So for all of these components, all of them are steady state. All of them are one inlet, one outlet. We neglect kinetic and potential energy changes everywhere. The compressor, the heat exchanger, so the condenser and the evaporator are passive. No friction losses, right? No heat losses, right? So if I'm trying to do the condenser, I get this equation. Q dot is equal to M dot times H out minus H in. Remember, we did this to find the mass flow rate, because when remember, there were 3 ways to find the mass flow rate. One of those ways was use the place where you know Q dot or W dot, right? So I can use that to find the mass flow rate. Here again, I might have to take an absolute value, right? Although it should work out, right? And here I'm just going to leave this, unless the problem specifically said pound mass per second. I could divide by 60, by 60 squared, I guess, right? Because 60 would be per minute, and then if I divide by 60 squared, then I get per second, right? But I just left it as 681 pound mass per hour. Right? Now, it also asked us for the compressor power. So just like for most compressors, right, they're all steady state, one inlet, one outlet, no kinetic energy change, no potential energy change, adiabatic instead of passive, right? So here we're going to get that W dot is M dot times H in, which is H1 minus H2. This is the real compressor, not the ideal compressor, So it's H1 minus H2, not H1 minus H2S, right? Here, again, this is going to give me BTU per hour, but if I wanted to change this into horsepower, right, then I'd need some kind of conversion factor, which I could look up on the equation sheet, right? So this is, my compressor power is just under 9 horsepower. Now, again, you never go into Home Depot and say like, oh, I want a compressor that's negative 9 horsepower, right? But we know as engineers that the negative value here means that you're putting power into the system, right? You're adding energy into, or you're adding power into that fluid to increase its enthalpy. The compressor efficiency, right, is going to be the ideal compressor power divided by the real compressor power, right, or H1 minus H2S over H1 minus H2. We fixed those states. Right here, again, you see that the delta H for the ideal compressor is less than the delta H for the real compressor, right? You have to find it that way, right? So you know that the power is less for the ideal case because this is a cost to the system. So here we found that the compressor efficiency was just about 61%. Finally, we want our coefficient of performance, which is the energy benefit over the energy cost. The energy benefit is that heat that we're pumping into the hot place, and the energy cost is our net power. So here we know you could calculate Q dot hot, but it's given to you, right? So it's like one more thing that I can screw up putting it into my calculator, or I can just take the value they give me, right? So that's what I did. I just took the value that they gave me. I put, to be safe, the net power as the compressor power plus the valve power, but the valve power is 0 because that's m dot times H in minus H out, but H in and out are the same for the valve, right? So that goes to 0. I don't technically need absolute value signs because it's a negative divided by a negative. And I see that my coefficient of performance here is 2.67. And that's how I do a heat pump problem. If it was a refrigeration problem, it would be almost exactly the same. The only difference is that the thing that I knew, or the thing that I cared about, the energy benefit for the refrigeration system is Q dot cold. Otherwise, it's all the same. You still fix all the states in the same way. You just do a different control volume when you're looking for the energy benefit. So that hopefully gives you a good overview of how to do refrigeration and heat pump cycles. But also, it means we're done with new material. So, like we said, next class, we'll do some problems that you bring in. Probably I'll do a little bit of a review at first, just to kind of remind us of the things that we need to do. And then that'll be it. So we got 2 more classes, and they're both review classes. So in addition to those cycle problems that we'll do, if you just have questions, you can always bring those to me in these review problems, or you could come to office hours, including tomorrow at 3 o'clock. So that's all I had for you. Does anybody have any questions? Okay, thanks very much, everybody. Have a great night.
Have a good night.
You too.